Good evening everybody. I am Priyadashini, Department of Mathematics in Sri Shanmuga College of Engineering and Technology, Salem. I am going to discuss about the topic is queuing theory. The topics are introduce basic of queuing theory, define notation and terminology used, discuss properties of queuing models, and the examples of queuing analysis are m/m/1 queue, variations on the m/g/1 queue, open queuing networks models and closed queuing network models. So the basics of queuing theories are: queuing theory provides a very general framework for modeling system in which customers must line up for service. For example, banks, restaurants, computer systems, networks. So the next one is queue-based models. Queue model represented arrival of jobs into system, and then service time, requirements of job, waiting of jobs for service. The last one is departure of jobs from the system. Next one is why we are using queue-based models. In many cases, the use of a queuing model provides a quantitative way to access system performance. Throughput, for example, job completions per second. Response time, for example, web page download time. Expected waiting time for service, number of buffers required to control loss. Reveals key system insights, often with efficient closed form calculation. The next one is, what are the assumptions we are using in queuing theory? In many cases, using a queuing model has the following implicit underlying assumption. The first one is Poisson arrival process, the second one is exponential service time distribution, third one is single server, and the fourth one is infinite capacity queue. The last one is first come first serve discipline, or also known as first in first out. The next one, advanced queuing models. There is tons of published work on variations of the basic models. Correlated arrival processes, general service time distribution, multiple servers, finite capacity system, other scheduling disciplines. We start with the basics. Queuing notation. Queues are consciously described using the candle notation, which is specific arrival process for jobs, service time distribution, number of servers, storage capacity, service discipline. Example models are m/m/1, m/g/1 and m/c/3. The model m/m/1 assumes Poisson arrival process, exponential service time, single servers, first come first serve service discipline, infinite capacity for storage with no loss. What are the notation we using m/m/1? Markovian arrival process in Poisson process, Markovian service time in exponential distribution, single server, first come first serve, infinite number of capacity. The next one is, we use the notation for arrival rate is lambda, inter-arrival times are exponentially distributed with mean 1 by lambda. Service time notation is mu, service times are exponentially distributed with mean 1 by mu. System load notation is rho, rho equal to lambda by mu, rho varies from 0 to 1. It is also known as utilization factor. Stability criterion, rho less than 1 for single server system. The next one is queue performance matrices. Capital N represented by average number of customers in the system as a whole, including any in service. Capital Q represented by average number of customers in the queue, excluding any in service. Next one is W is represented by average waiting time in queue. The next one, capital T represented by average time spent by a customer including waiting time plus service time. Next, using Little's law, capital N equal to lambda into T. The next, results of m/m/1 queue. Average number of customers in the system, capital N equal to rho divided by 1 minus rho. Variance of N equal to rho divided by 1 minus rho the whole square. Waiting time W equal to rho divided by mu into 1 minus rho. Time in system, capital T equal to 1 divided by mu into 1 minus rho. These are the formulas for m/g. m/1. The next model is m/d/1. The assumptions of this model is assumes Poisson arrival process, deterministic service times, single server, first come first serve service, discipline, infinite capacity for storage, no loss. The notations for m/d/1. M means Markovian arrival process. D means deterministic service times. 1 means single server, first come first serve, and infinite capacity. The results of m/d/1 model is average number of customers Q equal to rho divided by 1 minus rho square the whole divided by 2 into 1 minus rho. Waiting time W equal to x rho divided by 2 into 1 minus rho, where x is the mean service time. Note that lower variance in service time means less queuing occurs. The next model is m/d/1. Assumes Poisson arrival process, general service time, single server, first come first serve service, discipline, infinite capacity for storage with no loss. What are the notation we are using in m/d/1? M means Markovian arrival process, G means general service times, 1 means single server, first come first serve, and infinite capacity. So next one is results of m/d/1 model. Average number of customers Q equal to rho plus rho square into 1 plus C square divided by 2 into 1 minus rho, where C is the coefficient of variation for the service time distribution capital F of x. Waiting time W equal to x into rho into 1 plus C square divided by 2 into 1 minus rho, where x is the mean service time from distribution F of x. Note that variance of service time distribution would higher or lower for exponential distribution. The next model is d/d/1. Assumes general arrival process, general service time, single server, first come first serve, discipline, infinite capacity for storage with no loss. The notations of d/d/1 is general arrival process, general service time, single server, first come first serve, and infinite capacity. The next one is queuing network model. So far we have been talking about a queue in isolation. In a queuing network model, there can be multiple queues connected in series or in parallel. For example, CPU, disk, teller. Two versions are there. First one is open queuing network models. The second one is closed queuing network models. So what is open queuing network models? Assumes that arrivals occur externally from outside the system. The second one, infinite population with a fixed arrival rate regardless of how many in system. The next one, unbounded number of customers are permitted within the system. And the last one, departures leave the system. So what is the next one is closed queuing network models. Assumes that there is a finite number of customers in a self-contained world. Finite population, arrival rate varies depending on how many and where. Fixed number of customers that recirculate in the system can be analyzed using mean value analysis and balance equation. Thank you.